From the last session, the question was consider this sequence of 5, 555, 555, 5555, and so on. And then we start with this first question. Does there exist multiple of B7 in 2021 in S5? This was the question. So first, does there exist a multiple of 3 in S5? Does there exist a multiple of 7 in S5? And does there exist a multiple of 2021 in S5? This was the question that we were discussing. And let us now take up this case of 2021. Does there exist a multiple of 2021 in S5? Any comments on this before I proceed to the solution? Or with more hints? Any comments? Okay, fine. So if there are no further hints, if there are no further comments. So
Sir,
yes, sir.
Sir, here the 2021 factors are 43 and 47 you said. Early we know. But both are prime numbers.
Yes.
Then that's only further thinking will be blocked actually.
Will be blocked, yeah. Okay. But for 3 and 7?
3 and 7, okay, sir. Because I've seen the last this one.
Video, right? Yes.
Video I saying that is excellent. That is a 555. It is a pattern of we know that is a addition of numbers gives the multiple of 3 and everything. All multiples of 3 we can see, that is 3, 6, 9. All this divisible by 3. Okay, 7 we know the pattern, that is 1, 2, 3, 1, 2, 3. We can look at that one and we can manage divisible by 7 also.
Very nice. So for 2021, if you try to look into the factors, it becomes messy, right?
Yes,
so
sir,
we were trying to see if we can have a more elegant approach to this problem. And for that, I had given a few hints. First hint was, so here we have 3, 7, 2021. Instead of having that, we'll just take it as n. 3, 7, 2021 or any number. So if I have that n divides a number n1 and n divides a number n2, then, sorry. If what we saw was, if the remainder of n1 divided by n is some k, and remainder of some other number n2 divided by n, if this is also k, if both of them are equal, then we saw that n divides n2 minus n1. Was one. This is one thing that we know. And and I had mentioned about Pigeonhole principle. So we will see what we can do. Now let us take this sequence S5, 555, 555, 5555, and so on. 5555 and so on. Now let us take the remainders when we divide with remainders with 2021. Right. So what are the possible values the remainders can take?
Yes, 0 to 2020.
0, 1 to 2020. These are the possible values. Now, if 0 is taken by any of the number, then we are done, right? If one of the entries is 0 here, the remainder we are done. So here, but we do not know that. That's what we're trying to prove, and looking into its prime factors also is not an easy method to see if there are any 0 remainders. Okay, but we have this first observation here that if two numbers have the same remainder, then we know we can find the multiple of 2021 here. Okay, but that multiple is the difference of some two numbers. Right? So first question is, will remainders repeat here? Can a remainder repeat here, or is it possible that all the remainders are different? In the second row. In the second row, is it possible for a remainder to repeat anytime? So here for 5 it is 5, for 55 it is 55, for 555 it is 555, for 5055 then we have to calculate this is some number here. So question here is, in the second row, will a remainder repeat?
Yes, Shiv. There is a possibility that the remainder will repeat after 2020 terms.
Will it definitely happen, or there's just a possibility?
It will definitely happen.
Definitely happen. Why is that?
That's a tough question.
Okay. It will take some time.
Yeah.
Yeah. So one way to see it is by taking some small examples. Instead of taking 555, 555, and so on, we can take 1, 10, 100, 1000, 10,000, a familiar sequence, and then take a remainder with 7, and then see what happens there. Will a remainder repeat anytime?
Actually, it will repeat, Shiv. If you take 10, 100, 1000, 10,000, 10 to the power of 4, 10 to the power of 5, after and divide by 7, the remainders will certainly repeat.
Beta?
Yeah.
Okay. This is 7. There it is 3.
Yeah. 2, 6. Yeah. 4, 5,
and 1.
1. Yeah.
Right? So the remainder again, 1 is coming here, 1 is here, and the repetition is occurred. So can we give a reason of why a similar thing will happen in 2021 also?
It should repeat, Shiv, because the remainder cannot, it is bounded from 0 to 1 less than the divisor. So remainder cannot be more than the divisor, more than or equal to the divisor.
Correct.
So it has to repeat.
It has to repeat. So, right. So, in the language of Pigeonhole principle, how it can be said is, so here I recall the Pigeonhole principle. The Pigeonhole principle is, if there are 6 pigeonholes, and 7 pigeons, then at least one hole will have more than one pigeon, right?
Yes.
So this is a statement of Pigeonhole principle. So so can we visualize this logic here in this question of repetition of remainder? So what would be the pigeonholes and what would be the pigeons?
Yes, the remainders starting from 0 to 2020. There are 2020 pigeonholes, and all the sequence of 5s are the objects.
Are the pigeons?
Are the pigeons? Yes.
So how many pigeons are there? There are infinite pigeons.
Infinite pigeons. Yes.
They're not 7. There are infinite pigeons in 2020, and so at least one will have infinite number of repetitions. So a remainder, there will be one remainder which will occur infinite number of times.
Yes. Worst case, you can guarantee that a pigeonhole will have more than one, one pigeon or one whatever it is after 2020 term, right?
Exactly. So we can even say that within so this very simple looking principle is used very powerfully in combinatorics. So we will take this 2021 times. So we can be sure that this repetition must occur within this, right?
Yes.
The repetition must occur somewhere here itself. Some repetition. So what is the conclusion from this? There is some sequence of 5s having some remainder k, and there is another sequence of 5 having the same remainder k, right?
Yes.
Right. Now, using our initial observation that if two numbers have the same remainder, then we can say that n divides into minus n1, right?
Yes.
Right. So now, what can we say?
So you can take the difference of any two, let's say, terms, and that difference is divisible by
Any two.
in the sense like having the same remainder.
Any two having the same remainder. Okay. So now
Having the same remainder.
if these two is giving the same remainder of k,
Yes. Then
what
take difference.
we can take that difference and we can say that the difference it will be of the form 5, 5, 5, 5 followed by zeros.
Yes.
Right? So
Yes.
we know that 2021
Divide
this
by
number.
some.
So we know that 2021 divides this number for some number of 5s and some number of zeros. Okay, so now from this, what can you say? So the initial question is, does there exist a multiple of 2021 and sequence S5? But here this number 5555 .000 does not belong to S5. Okay.
But
Yeah,
since
so
it is a multiple of 10, I think 555 follow into let's say 1 followed by some zeros.
okay. So let us take this k zeros, k5s, and some m zeros. So we know that 2021 divides this 5555 into 10 power m. So here what we have is 25 into something is equal to 500. This is the meaning of 25 divides 500. Now, when we want just 25 and 5 to 100, if you're able to cancel out this 100 with this box, then we'll have only 5 in the right hand side and 25 here, and we can say that 5 will be divisible by 25, but the cancellation is not possible here. So what we have here is, from the first statement, what we have is 2021 into something is equal to 555k times into 10 power m. We have 2021 divides this number having k5s and m zeros. The question is, does 2021 divide this number having k5s? So we'll give a nice example. 25 divides 500, but 25 doesn't divide 5. This is an example where this fails. I take another number, 7 divides 3500, and it happens that 7 divides 35. So in some cases it seems to work, in some cases it's not working. Can we tell where it will work and where it won't work?
Shiv, if we can show that 2021 doesn't divide a multiple of 10. 10, it should divide. It should definitely divide the K5s which you are talking about. That means 2021
Okay.
and the multiple of 10 does not have a common factor.
Is it true? Do they have a don't they have any common factor? So instead of multiple of 10, it should be power of
Yes,
10.
yes, yes.
Right?
Power of 10.
Nice.
Yes, Shiv, I think 2021 doesn't divide power of 10. So definitely it should divide K5s because 2021 has factors 43 and 47, whereas let's say 10 to 10 to the power of something, it has factors 2 to the power of something and into 5 to the power of something. 2 and 5 has factors. So certainly there are no common prime factors. So 2021 should definitely divide K5s.
Exactly. Right? Yeah. So as you said, looking into the prime factors will always help. Looking into the factors. So here we have 2021 into something is equal to 555 into 10 power m, and this 10 power m can be written as 2021 into some number is equal to 5 into 2 power m into 5 power m. So we have in right hand side 2 power m and 5 power m, and in the left hand side also we need to have this 2 power m and
Yes.
5 power m somewhere. If you break it into prime factors, and we know that 2021 doesn't have 2 or 5 as factors, so both this 2 power m and 5 power m has to come here. It has to belong here.
Yes.
Along with something else, right? And so yeah, and so this 2021 must divide. Yeah, so again going step by step, we have this 2 power m, so this contains 2 power m into 5 power m. Now let us remove this 2 power m into 5 power m both sides. So we'll have 2021 into something dash is equal to 5555. So I've removed divided by 2 power m into 5 power m on both sides, and this shows that 2021 actually divide. Yes. Or this is one way of seeing it in the form of prime factorization. Okay, so yes.
So we can say that 2021 and the power of 10, they are co-primes, right?
Yes. Right. So have we solved our question?
Yes. Yes.
Right. So now we have that some multiple of 2021 present in S5. Okay, you're right.
Yes. Yes.
Now, for what other numbers will this work? Can we make a general statement? For what other for what all years? So now this year being 2021, we took this year. So can I say the same thing about the next year? About 2023, 2024, like for which all years can we be sure that this property holds?
Shiv, for all those numbers, that does not divide power of tens.
Exactly. For all those numbers, which are co-prime with n. Can I say that?
Yes. Co-prime, relatively prime, co-prime with power of 10.
For all the years which do not have 2 or 5 as factors, we can be sure that
yes,
this is the case. But for numbers having common factor of 2 or 5, what can we say about that? If a year has some factor of 5 or 2, then can we say that it will not occur, its multiple will never occur in S5?
we cannot say that.
Exactly, we cannot say, right? Can you give an example of a year which has either 2 or 5 as a factor, but which has its multiple in S5?
2 and 5 has factors.
Either 2 or 5 as factor,
Okay.
but whose multiple is in S5.
Okay.
We can go to 555 AD. This is already there in the ecosystem directly.
2020 has 2 also has factor, 5 also has factor.
Okay, so 2020. Okay, so after 2020 has both 2 and 5. Then can a multiple of 2020 occur in S5? Can a multiple of 2020 occur in S5?
I mean, 2020 has factors other than 2 and 5 also. So that's the point.
Yes.
So only those numbers that have exactly 2 and 5 as factors.
No. That was not my question.
So what about 2000, sir?
What about 2000? Yeah, what about 2000, sir? Oh, yeah, what do you think?
Then it is factors of 2 and 5 both.
Yes.
And again into 2 into 5 into 2 into 5. 2 into 5.
It is 2 into 4 into 5 cube.
2 into 5. 2 cube into 5 cube. Yeah. 2 cube into 5 cube.
All those numbers that have say exactly 2 and 5 as factors, only 2 and 5 as factors, we cannot say that those numbers divide the sequence of 5s. We cannot say.
Oh, we cannot say, or they won't divide.
Pardon?
Are you saying they won't divide a number in S5, or you're saying we cannot say?
We cannot say.
We cannot say. Okay, so for example, if we take this 2020, can a multiple of 2020 occur in S5?
No, 2020 has factors other than 2 and 5 also.
Oh, okay, fine.
It has 2 and 5 also has.
Okay, fine. So if you take 2000, okay, if you take 2000,
it has exactly 2 and 5 as factors.
Correct. So
we cannot.
Can a multiple of 2000 occur in S5?
We cannot say.
We cannot say, but we can,
because 2000 completely divides the power of 10. We cannot say that it divides the sequence of 5s also.
Okay. But one thing we can say, we can say what the last three digits of multiples of 2000 are. Right? If you look at the multiples of 2000, we know for sure what the last three digits are. Right? What are they?
They're always zeros.
They're always zeros. But S5 always has 5s.
Yes.
So yeah, so you're trying to look at it through the proof argument. So right. So again, so for which all years does this property hold? For one thing, for all the years which do not have 2 or 5 as factors, this property holds. That is one clear observation that we have made from the proof. So the proof is just using one simple observation and this principle of Pigeonhole principle, and we are able to make a even more stronger statement, not just for 2021, but for any year. So any year not having 2 nor 5 as factors will satisfy this property. Okay. So then, what about years which has either 2 or 5 or both, or only 2 and 5 as factors? What can you say about them? Can we characterize all the years which holds this property? So can we characterize can we characterize all the years having this property? You can think about this. You can spend some time thinking about this after the session. So here, let us just go back here. With a simple observation and this use of Pigeonhole principle, we have been able to get quite a powerful result, right? So for small numbers 3, 7, 9, and all, we were using the divisibility test, right? But when the numbers become big, using the divisibility test and following the remainder cycles, challenge. But here we are just observing the remainders, and by Pigeonhole principle, we see that in S5 there must be two numbers in S5 having the same remainder, and then their difference, and then further analysis gives a multiple of that 2021. And we also saw that we can generalize this proof and get. So I mentioned this that there are several interesting applications of Pigeonhole principle. So I thought of giving another very interesting problem that this Pigeonhole principle comes up. So there is this club. There is this club here, and people come. So at a given point, so when the club opens, certain number of people come in, and they play cards. So certain number of people come in. A person chooses a person randomly and plays a game of cards with him or her, and then he chooses another person and he keeps on playing as much as he wants, and then once he is done, he stops. Right? So a group of people enter, they choose their opponents one by one. They choose their opponents. So it's a game where just two people play against each other. So they come, they choose their opponents one by one, and then after they play and after they feel that they're done, they just leave the club and go. Sometimes it might happen that a player might just stop with one game, or it might happen that a player doesn't play in any game at all. So it is up to the player. And this club has a rule. This club has a rule saying that so after everybody is done playing with the opponents, and one more rule is a player does not play with an opponent more than once. So a player doesn't play with an opponent more than once, just once, or 0 times. This is the only condition. Otherwise, it is just arbitrary. You can play, and as I said, the player can choose not to play at all any game that day. So this club has a policy. The policy is it counts the number of matches each player has played, and if there are 2 or more people having played the same number of matches, so if 2 or more people have played the same number of matches, then all of them get a gift. All of them get a gift from the club. Get a gift from the club. So this is the club rule. So this rule has been there for some time, and the owner has changed. And the owner, this new owner, he sees that okay, if 2 or more people have played the same number of matches, then all of them get a gift from the club. This new owner doesn't want to give away gifts. So he decides, okay, let me fix the matches. So let me not make them play randomly. Then it might happen that 2 or more people might play the same number of matches. So let me fix the matches, but it won't be apparent to them. It won't be apparent to the people who enter the club that these matches are the opponents are being fixed. But somehow he will control the opponents so that each and every player has played different number of matches. Okay, so this is what he's thinking, and he was just wondering of how he will do it. If so many people come, how will he allot the different matches? He was just thinking, and to his relief, on that day, just 6 people enter. On that day, just 6 people enter. So now it becomes easy for him, and now he thinks that it becomes easy for him to schedule their matches so that in the end, every player has played a different number of games. Okay. So now, but still he's confused. If you want to help him, how will you fix those matches between the 6 people so that everybody get different number of matches? This is the question.
Sir, is it like handshake problems?
Okay, so you're making an analogy between this and the handshake. So what is the handshake problem, sir?
No, if one person is there, how many he can play handshake? And if it is 2 members are there, how many handshake takes place?
Oh, okay.
Then, like that, if 6 members are there, how many games they play with each one like that? I thought it's similar to that. I don't.
Yes. There is some similarity there because a handshake is we can map handshake and 2 players playing a game. Yes.
Yeah.
It feels like it's not possible.
It seems that it's not possible. So can you prove it? It'll be always easy if you're able to model this problem somehow, right? To visualize and see.
Yes.
There are 2 ways of So can you tell some ways of modeling this problem for visualization? How did you model it?
So it is like a triangle, pentagon, all will come, sir. That is one is one line,
Yes.
square, triangle, square, pentagon, like that. If you go on tracing that.
Right. So you can consider the 6 people.
Hexagon, then
and then if 2 people, if they're having a match, you can draw it.
Yeah.
So if everybody plays with everybody else, then there will be 15 matches.
Yeah.
In total, yes. 15 matches in total. And if everybody plays with everybody else, then what is the number of matches each one
15
plays?
matches. Each one will play 15.
5.
Exactly.
5.
Each one will play 5.
5, yeah. Right? One less of it. Yeah.
So now the club has to, if this is the case, the club has to give praise to all of them.
Yes.
Right? Yes. So this is one way of. So this is in math. This is called a graph, having this kind of a representation. We can also use a good old table to model this. You can have player 1, player 2, player 3, player 4, 5, 6, and so on. And 3, 4, 5, 6.
You want with 6, I think.
3, 4, 5, 6. So P1, P2, P3, P4, P5, P6. So if there's a game between 2 people, you can just put a 1, otherwise a 0. Right? So here, this model is you have the model which you told here. The schedule that you just now mentioned is once everywhere, except the diagonal. The diagonal will be 0, and the rest will all be 1. Okay, but here each player is playing 5 times. Okay, now let us just look at this. We have this player 1. This is the player 1 and the number of matches. The number of matches. Player 1, player 2, player 3, player 4, player 5. Okay. So again, what are the possible number of matches he could have played? Try to think along that line. Sorry, and player 6. So now we have 6 players, and the number of matches. What is the set having the possible numbers?
So that each one plays a different number of matches, right?
Each one plays a different number of matches. Yes.
First one will play 5, 4, 3, 2, 1 comes like that, no, sir?
5, 4, 3, 2. Okay, we'll just keep this. 5, 4, 3, 2, 1. Then player 6.
then it comes
0. I mean,
0.
it does not
A
play.
player may not play a single game also. That's also
single
possible,
game.
right?
Yeah, that is 0.
This is perfect because the total adds up to 15 matches. 5, 4, 9, 9, 3, 12, 12 plus 2, 14, 14 plus 1, 15.
Yeah.
So does this mean that there are 15 matches? So here, if you look at this case 1, here if you take a total, the total is 30, right?
Yeah, but Shiv, this 30 includes the case where a player plays with an opponent more than one time.
No. So here, if you see this 5, 5, 5, 5, 5, 5, this is the each player is playing with every other player once.
Yes, Shiv. Yeah.
Just once.
That's correct. But Shiv,
Right.
P1 plays with P2 and P2 plays with P1 also. We have marked that also as 1.
Correct.
Right? P1
Correct.
plays with P2 and P2 also plays with P1. We have marked that one also.
Correct.
That means P1 is playing with the same opponent. Opponent.
Correct. So we are double counting certain number of matches, right?
Yes.
So if you the total is 30, but the actual number of matches is
actually 15.
15. Because we are counting P1 versus P2 and P2 versus P1 both. Right? Very nice. Actually 15. Okay, now since you told total, that's a very interesting thing to consider. So total, what is the total here? 15.
15.
Right? If total is 15, then what is the actual number of matches?
15 only, sir, matches.
Oh, here the total and the actual number of matches both are 15, huh?
Yes, sir. Yes, sir. That is the number of matches. All together, 6 will play. All 6 will play. If we play one at a time, one with one opponent, then 15 matches will be there.
But here, in this scenario, if you take the sum, it is 30. But there are not 30 matches now. Nice approach, sir. You can try to draw this sides in this hexagon to see that the actual number of games they have played. So it is not. So it is the total number of games they have played in the end. So each player is counting for himself. Each player is counting for himself. How many matches he has played totally, and that is the total number of matches. And that should differ from the number of matches played by other player. So this is one way of trying to solve this. And Sunil took this total. He made a comment. Sunil made a comment about total, no?
Yeah.
15, right? 15 is a total.
Yeah.
So from this, can you tell anything about the actual number of matches played?
Is it less 15 minus 5? Is it 10?
Okay. Minus 5?
I mean, since we are like, I thought we are counting twice. Because since let's say P1 has played 5 matches, he has played 5 matches with other 5 players. So while considering P2, we are again P2 has of course played 4 matches. So probably we are counting twice.
Okay, so you can think about this relation. And Jagdish sir, you can try to complete the hexagon to get this case where each vertex has different number of edges coming out of it, basically.
Sure, sir. I'll try, sir.
That is equivalent form in the hexagon.
Yes, sir.
And we'll
but it won't be hexagon, I feel. Then that time, if the current, if it doesn't form hexagon, only some open figure it comes. Open. I feel like this.
Yeah.
Not.
So, and earlier, Gauri ma'am also made on comments saying that it is impossible. It seems impossible. So we should also take that into consideration also, whether a solution exists or not. Because for all the problems, it's not necessary that a solution exists. So this problem, what is the scenario? That so we'll keep that option also open, right? And if a solution does not exist, why not? So that is another thing which we can keep in mind.
Okay.